It'll be the same slide on both sides.
Okay.
Yeah. Okay. The slides are all in serial order.
Got it.
Okay, so we got Oleg, we got. Oh, you're the first up. So get over there. But actually, okay, good strategy is that. So Oleg comes out. Eric, you may as well just get pre-positioned. As soon as Oleg leaves, then
Bam.
Zack, comes up and pre-positions himself. So you're all set. Okay.
Okay, can I have my 30 seconds? Yeah.
Okay.
Hello and welcome to the Planetary Science Institute Retreat. We are coming to you live on twitch.tv/CosmoQuestX. Please share that link out. I have already done so you do have an audience to which, if you don't get off the stage fast enough, they will see your public humiliation. It is now public. The music that you heard prior to us going live came to you from David Joseph Wesley, who has given us permission kindly to use all of his music. I am now going to step back and let the chaos start. Thank you.
Okay, good afternoon. My name is Oleg Abramov. This is a picture of my backyard in New Zealand. It has a lot of plant life, as you can see, and the question that I'm posing is, what is life? Now, we all have some intuitive feel for what life is, but it turns out it's very difficult to precisely define, and there have been several efforts to do so. It either ends up being too general and it ends up including things like fire, which is not really life, arguably, or too specific and includes things like organic chemistry, or Darwinian evolution, which is too specific and perhaps biased to our terrestrial life. So is there a better way to define life? Perhaps there is. Like I said, there is a number of efforts already, and maybe it's possible to distill them using conceptual modeling into a better definition of life that's based on processes rather than structures. Thank you.
All right, it's my turn. Two things. First, PDS. We have figured out how to archive pretty darn well. Now our focus is getting the data out to people. That's one of our major emphasis. And in general, if you're interested in dust or asteroids, talk to me. Second thing, OSIRIS-REx. We were supposed to find an asteroid that had 50-meter diameter spot to collect a sample. Turns out we're about like 8 meters. So we are actually using a feature called natural feature tracking. We will be building, my team and I will be building very small features, DTMs. We upload to the spacecraft, it will follow it automatically, and we're going to go down to a resolution of 0.5 centimeter. Thank you.
Wow.
Take the time, Zach. Take it.
Go!
Oh, okay. I'm Zack Fane. I work in the Colorado office as a research assistant. I was somehow convinced to defer starting my undergrad to work on the subsurface water ice mapping project. And then over the summer have been working on using, all with Sherrod. I work with Sherrod. Okay, I've been working on looking at layered ejector craters in Sherrod. And then I actually just started my undergrad at Colorado School of Mines last week. And I'm now half-time at PSI.
Any questions for Zack?
Hi, I'm Neil Pearson. I run the spectroscopy lab here in the Tucson office. We have spectrometers ranging from the vacuum UV all the way out to the mid-infrared, and we're going to extend out to the thermal infrared here in a couple months. If you want to use any of the equipment, contact me. We also have a field XRD, XRF, and we're also getting a viscometer soon. We also have vacuum chambers, vacuum pumps, liquid nitrogen, and all that sort of fun stuff.
Hello, I'm Dan. I'm a senior scientist. This is my 21st year at PSI. Feel free to come up to me and say hi, introduce yourself. I can be shy, but I'm friendly, I promise. I am interested in fluvial, glacial, volcanic, and alien geomorphology, all those good things. I am an expert in crater counting and planetary chronology. I am a geologic mapper. I've done maps on Mars and Moon and Vesta and Ceres. I'm an expert in GIS. I can answer any of your GIS questions. I'm here to help. I also do DTM production using both SocketSet and the AIM stereo pipeline. I have some beautiful examples of my work here. A geologic map I did of Mars, and some ice-rich features on Mars, and some alien features. Thank you.
Hi everyone, I'm Tom Friedman. I do planetary nuclear spectroscopy, which is the application of nuclear instruments and methods to geology. There's a picture of me on the upper left in a cave, so I also do some Earth-based field work. And I want to draw your attention to the chart on the upper right, which shows a temporary exhibit that we did with the New Mexico Museum of Natural History and Science, which is just closed. It was up for 2 years. And it potentially has been seen by 500,000 people. So if you have a chance to collaborate with your local institutions on outreach, I encourage you to do so. Not as popular as Meow Wolf, but it was certainly a popular attraction in Albuquerque. For research highlights, we're continuing to work on Dawn. We have funds to work on an extended analysis program to analyze the beautiful data set that we acquired at low altitude at Ceres. This data set has allowed us to hone in on the... See my research.
Good morning. I'm Sam Webster. I work in our education group, and today I just want to tell you a little bit about La Space, which is an awesome program done by the Lucy mission. It's about training undergrads. This is run out of Arizona State University, and we get to do a piece of it. And we are targeting undergraduate students at minority-serving institutions primarily. They've had over 1,000 people go through an online program where they're learning about what it's like to work at NASA. They have just finished their first summer of internships, which is incredible because I'm talking to people who were homeless or who really never thought they would have a chance at a NASA internship. If you are asked to participate, it would be fantastic to have more scientists participate in this program. In my last 10 seconds, I'm going to make a push. We have meteorite kit training tomorrow. Larry will be leading it. Please join us. Thank you.
I'm Julie Rothman, and what I've been working on mostly this last year, I've been doing a lot of diversity and inclusion work in planetary science. I'm the chair of the DPS Professional Culture and Climate Subcommittee, which is their basically diversity committee. I've got a poster up on the wall over here on how is equity, diversity, and inclusion like quantum mechanics. I've given this talk at OPAG and at the Cornell Astronomy Department. And I'm hosting a diversity breakout session this afternoon for anyone who would like to learn more about diversity, equity, and inclusion in planetary science. Otherwise, I love Io. I love Io's volcanoes. I've been doing ground-based observations at the IRTF. We found something pretty bright on June 25th. The location is shown there in that image. I wish I knew which one it is. And I've been working with Jeff Morgenthaler to compare this to the Io Taurus. Just got enough to study the Juno J-ROM data.
Hi, I'm Roger Clark. I do spectroscopy, searching for the composition throughout the solar system, including the Earth. And a big problem in planetary science and spectroscopic remote sensing is trying to match a very large range spectrum. So in this case, here's ice, and it's very hard to simultaneously match the spectral properties at the long wavelengths, the visible wavelengths, and the UV wavelengths. And that's because models haven't worked with changing composition and grain size with depth. So I've extended radiative transfer models, solved the equations, and now we can do that. So we can match the band depths at the shorter wavelengths than we could ever before. So, and this says a GUI radiative transfer is under development. That's actually complete.
Hi, I'm Nalin Samrasinghe. I primarily work on comets. Comet nuclei and coma. I looked at the physical properties of the nucleus, rotational properties, and when it comes to coma, the coma morphology, what we can tell from that. These are different projects that I'm involved in. And also I have developed image enhancement facility which is available at PSI website. So if you have coma images that you would like to enhance, you can use that facility. Okay.
All right, one day we're going to send people to Mars, and when we do, they're going to need water for life-supported refueling. So I like to use geophysics to look for water ice in the subsurface of Mars. Specifically and currently, I do numerical simulations to connect geology to data from the Mars Reconnaissance Orbiter's Shallow Radar Instrument. I also like to do numerical simulations for instruments that don't exist yet. So I'm helping design the Autonomous Roving Exploration System. So it's a large rover that's going to drop a weight on the surface, create a seismic source, which will then be recorded at receiver rovers, and create high-resolution 3D images of the subsurface, which will be necessary for resource surveying. I'd also love to talk with any of you about the science you could accomplish with that system. And since I have 5 seconds, my name's Sam.
I'm Robert Schroehofer, and one of the questions I'm working on right now is how many cold traps are there anymore? Right? The basic question. And most of the cold traps are very small, they're sub-resolution for an instrument. So this is a big exercise in statistical topography, right? So you take temperatures and then use extrapolations to extrapolate them to smaller scales, or you use a camera image, measure how many shadows there are and extrapolate that to smaller scale. And you translate instantaneous shadow to permanent shadow. And so it's a big quantitative exercise. And the answer is here is at least 10 to the 10 or so. So among the 10 to the 10 there must be a good spacecraft target.
I'm David Crown. My research is in planetary volcanology and geological mapping. The map that you see upper center there is a map of flow fields in southwest Tharsis, south of Arsia Mons. The ages that we've derived from crater counting are shown both in black on the map and then color-coded to the left. The pink and blue units that you see there comprise an intermingled, very young, late Amazonian flow field. And bottom left corner, you can see a dark, smooth lava embaying a levied, rugged lava flow. These are the two types of units that we're seeing. The dark lava displays characteristics that I think are essentially analogous to Hohoe lava. They're thin, runny fluid. They show evidence of storage and secondary breakouts, and also inflation. Thank you.
Hi, my name is Hannah Sizemore. I'm basically interested in any science that combines ice and dirt. Today I'd like to talk briefly about a topic that's been near and dear to my heart for a few years, which is unfrozen water at very cold temperatures. So if you look at the plot over here on the right, unfrozen water usually occurs due to intermolecular forces at the interface between minerals and ice, or at the interface between ice grains. It can occur down to temperatures of -30 degrees. And it's most abundant in cases where you have an intimate mixture of ice and soil. I came to start studying this through the numerical modeling side, basically looking at Martian frost heave and habitability of shallow ice. I've gotten involved since in a lot of lab work to understand the properties of this unfrozen water better. And if anyone would like to talk to me about that, please come see me. Thanks.
Hello, I'm Deborah Bang. I'm a senior scientist here at PSI. I'm also the deputy director. So if you do have concerns, issues, topics you'd like to bring up, you can either go see Dad Or you can come see Mom. But first and foremost, like all of you here, I'm an explorer. And that's where I get my kicks. And my latest area of exploration is asteroids. I've been privileged to be part of the Hayabusa 2 science team, and these are the images you see here. The one on your lower right is of the crater that the spacecraft created. That was one of the experiments on board. They have later sampled this crater area, so we're excited about getting the samples back. Mostly what I do is study the squiggly lines on the bottom. I help create a... I'm waiting. All right, Sarah, your turn.
Hi, I'm Sarah Sonnet. I spend most of my time divided between two different projects. In the first, I'm looking at rotational light curves of Trojan and Hilda asteroids that actually might be binary systems. So we're collecting the data, phasing the light curves, and gleaning solar phase functions, using that to determine shapes and constrain density. And from that, we hope to connect the density to possible formation location and help discern between competing solar system evolution models. Most of the rest of my time I spend working on the NeoCam survey simulator. You're going to hear a lot about that. But basically what I've been doing a lot lately is running the prototype simulator. I've been changing the cadence and seeing how that affects what we end up being able to detect. And that's it.
So one of my passions for the last more than a decade has been exploring the interface between machine learning and spectroscopy. And most recently, we did this proof of concept project where we're looking at asteroid taxonomy. For those of you who are familiar with the Bust-Amayo system shown at the left there, it's not very qualitative. It's not very quantitative. It's not a great classifier, and in fact, the automated version of it only classifies 60% of objects without visual inspection. So machine learning does a great job in situations like this where you're looking at wiggling lines. And so we spent the last 2 summers collecting data on 1,623 meteorites and 694 asteroids. We've reformatted all of it so it's in an identical file format with the same headers, and we're using the meteorite models to predict asteroid distributions, and the results are really exciting. And if you're interested, come and see me.
Hi, I'm Jordan Stekloff, research scientist here, and I work on a lot of different projects from Mercury out to Pluto, looking at geophysics, limnological processes, atmospheric transport. One of the projects that I'm working on lately is trying to understand what might be driving comet activity far from the sun. One idea that's somewhat controversial is that this might be driven by the crystallization of amorphous water ice, which can release either volatiles or heat when it crystallizes, amorphous water ice being like a glass. And this is thought to have formed in the early solar system. And the problem is, early in the solar system, there was giant planet migration, which should have triggered massive collisional evolution of these icy bodies. So we want to understand, would this destroy the amorphous water ice? So we use the ISAIL hydrocode to simulate impacts between large bodies. Then we ran it through a quick script to calculate the crystallization of amorphous water ice. And what we found is that, surprisingly, even when these things are hitting each other and destroying themselves, nearly all of the amorphous water ice can indeed survive.
All right. I'm Amber Grov, and I'm actually a technical document writer for the NeoCam survey simulator and survey planning tool. I have my library science degree, my master's in library from Indiana University. Mostly what I do is copy editing, maintaining documents for the NSS. I'm working on about 8 documents right now, copy editing, sorry guys, I'm so nervous. I was like, I have this in my head, I know exactly what I'm gonna do. Anyway, I maintain the documents on org because there's 8 people on our team. And so taking everybody's contributions, their figures, their text, their tables, sometimes I actually have my own tables and figures based on what's been handed down to me, information-wise. I love being here, thanks.
Hello, I'm Xiaodan Zhou. I'm actually more nervous than her. Yeah, where am I? So I'm now working on Osiris-Rex, working for them. I work mostly on the photometry for the obvious instrument. And I also work on another paper on comparison of different comet surfaces. And I'm also leading a project that help PDS improve the geometry backplanes for the Rosetta mission, mostly the images. And I think my presentation is the cutest because I also designed children's book already.
Hi, I'm Candy Hansen. I'm in charge of the JunoCam visible imager on the Juno spacecraft. Juno is in orbit around Jupiter, 53-day elliptical orbit. So once every 53 days, we get a bunch of fabulous pictures of Jupiter. This is an outreach camera. It does not have science requirements. And so our requirement was to make it accessible to the public. And one of the beautiful surprises that we got was how the public echoed back to us. So on your lower left is what we post on the website. Next picture over is an image that has been flattened with an experimental phase function developed by Gerald Eichstadt, art from Sean Doran, and the final image there by Lucy West is actually an oil painting.
I'm Brian Travis, a senior scientist at PSI. My focus is on theoretical and numerical models of chemically, thermally, and mechanically driven fluid flows and fluid-like flows. Applications range from looking at briny, icy convection in the Martian shallow subsurface to detecting, using machine learning techniques, to source of gas leaks, methane leaks on Earth. To more recently, looking at high-resolution simulations of convective processes in water-rich bodies like Ceres, and trying to relate those possibly to features seen, for example, in Arcturus crater with bright spots. Anyway, thanks.
I'm Jeff Cargill, and I work on applied and basic earth science of river blocking landslides and lake-assisted melting of glaciers. I also work with Sugata Tan on liquefied natural gas lakes on Titan and solid vapor equilibria. I work with Alexis on Mars ocean and tsunamis, and I hope to get into planetary science analogs on Earth. So now, 30 seconds of science. Drones and gyrocopters image ground chaos from helichoppers. Research glacial lakes from my kayak. Hazards, fieldcraft, science maniac. Methane, nitrogen, and LNG. Sugata, Titan's lakes, OMG. Alexis, tsunamis, Mars oceans, they stir reviewers' high emotions. I try and wish for funds and P-Star, wanna do field work here and there.
Jane Vanlin, one of 3 people on the Kelvin instrument for MSL. There are many mineral threads we could pull. I just want to look at 2 of our minor phases here that still have significance. One is acacaneite, which is an iron oxide hydroxide structure cropped open with chlorine. We have found it. It is commonly a precursor to hematite. And one question is, how much of our hematite might have had an acid oxide hydroxide precursor? The second mineral, tritonite, is really my favorite. We did not expect this at all. It's a common phase in high temperature, low pressure igneous systems that are very silicious. So our initial paper on this suggested acid volcanism on Mars. I'm pursuing another idea, probably very crazy, of silica from impact-rich vapors, impacts. Some of that silica has to go somewhere. Could it form tritonite?
Hi, I'm George Kramer. Okay, upper left.
The moon, and there's dark areas on the moon are called Mare basalts. They are basalts, they are volcanic. They flowed into low-lying regions. Look at the upper right. That is a topographic map of the moon. These are low-lying regions in the blue. But they also have compositional differences from the highlands. So you can see in this lower right one, which is a titanium oxide map. And in particular, Tranquillitatis, very famous for Apollo 11, is a high titanium Mare basalt. But something else that's weird about Tranquillitatis, it's not a low-lying region. Look back up where it's circled there. It's the same kind of elevation as the highland regions. So what's going on? How on earth did these Mare basalts get up onto this high area? Well, so now we can take a look at this gravity gradient map, and we see that there's something strange going on. It seems that there's some sort of giant rift that's reaching deep down into the mantle. So I am working on Pat McGovern's project to look at this.
My name is Kevin Webster, and I study astrobiology and biogeochemistry. I'm really interested in how we can look for life on other planets, and so one of the main ways I've been doing this is to look at caves on Earth. Caves are great extraterrestrial analogs. They lack sunlight and they have very low nutrients, as we might find on a place like Mars. So here I'm showing a cave that I did a lot of work in southern Indiana. And I'm showing some of my hopes and dreams for future missions. So I'm interested in potentially working on the remote sensing of caves and cave air. Here I'm measuring the methane concentration in cave in Kentucky. This is actually Mammoth Cave. And here's a CO2 instrument I work with, and hopefully we can, into the plot on the right, there is a graph showing that cave air in black is significantly different than the atmosphere in blue.
Hi, my name is Lucy Lepore. So I spent most of my time this year processing images of near-Earth asteroids observed by spacecrafts. So you can see a few examples here where I used sets of color images, for example, on the upper left of asteroid Ryugu, and build some maps or mosaics using those images. And with this, I study the composition and what we see, what units we see on the surface. And we have an example on the lower left of data from the approach phase of asteroid Bennu. And next to it, there is a really dark boulder. So we see interesting albedo differences on Bennu, much larger than what we thought we would get. And on the right side, it's another project I'm working on, processing images of asteroid Itokawa and doing color maps. And that's it.
Okay, I'm Paul Weissman. I do mostly comets, and this is actually where I started doing Oort cloud dynamics and trying to understand the evolution of long period comets. And these are not from my thesis, by the way. But at the top left, you see a plot of the semi-major axis, inverse semi-major axis of long period comets before they entered the planetary system, because once they were entered in the planetary system, they are scattered by Jupiter and Saturn. So you see the big spike, which is proof that there's an Oort cloud, and the other comets in the diagram are returning comets that are coming back for a second, third, or fourth time. There's a few comets that are hyperbolic. You're kidding me, it goes that fast? Anyway, the problem is there aren't enough returning comets, and I'm working on the physical loss mechanisms that remove comets.
Hi, my name is Emma Lilly, and I love asteroids. I spent the last 10 years of my life working in Hawaii for the Pan-STARRS survey, pretty much defending the Earth from the dangerous asteroids that might come at us. And I recently joined the ranks of the NEOCAM team, hopefully getting some, when the mission gets funded, we're going to be looking for dangerous asteroids in the infrared and hopefully seeing more of them, because it happens, as it happened during my time in Pan-STARRS, the little impacts of asteroids happens mostly when I'm on vacation or maternity leave. And the second part of my time, I would like to dedicate for Centaurs. We are really cool big asteroids that come from beyond the Kuiper Belt, and as such, they bring, like on a silver tray, all the primordial organic material and cool exotic ices, back closer to us so they'll be studied. I'm hoping to dig in the PanSTARRS database for them.
Hi, I'm Annie Wilson. I work with Dr. Pamela Gay and Susie with CosmoQuest. I do community engagement. I am also not a scientist, science streamer on Twitch, where most people go and watch other people play video games. I'm not joking, this is a thing. I do data visualization. By that I mean I like colorizing Hubble images, and I like space toilets. So there's 6 humans in space, there's 4 toilets, 2 are on the ISS, 2 are on Soyuz. That there is no toilet on the Soyuz that Skybot's on. They figured the robot didn't need a toilet, and all the toilets are of Russian design, and there's been 140 toilets that have re-entered the atmosphere. Over 140 toilets that have re-entered the atmosphere, and 13 of those were space stations, and oh my goodness, what's happening?
I'm Scott Mist. I'm a senior scientist here at PSI. My main interest is planetary geologic mapping. In the upper left is a 3-quad geologic map of an area on Mars. In the kind of to the lower right is a global geologic map of Ceres, and in the lower left is the south polar quad of Mars, LQ30, or excuse me, Moon. I love mapping different terrains, different planets, Mars, Moon, Vesta, Ceres, and part of Mercury so far. Always looking to expand territory. I do all my geologic mapping in ArcGIS. My interests, additional interests, are fluvial, glacial, impact, volcanic, and aeolian geomorphology. And I've also done a lot of crater counting and planetary chronology in the past. Thank you.
Hi, my name is Chun. I'm a software programmer for PSI. I'm currently part of the NeoCam dev team. I recently graduated from University of Arizona with a computer science degree, and some of the stuff that I've been working on is converting our flat file input and output to database. As you can see on this graph over here, blue line is the flat file running time, and then the orange line is the database. I was able to improve 90% at 900,000 objects, and also on top of that, I've been working on a lot of unit testing for quality control. And I want to say thank you to Tommy for giving me this opportunity for working with you, NeoCam, and yeah.
All right, hi everybody, I'm Susie Murphy, and you've heard of CosmoQuest several times today, I'm sure a few times. And one of the things that I am here to do for you is to get your science out on podcasts and interviews. So there are people out there who really want to hear about whatever you are doing. And so we want to get you the opportunity to be on various podcasts, to be on live streams, to be on our Twitch streams. And we want people to be able to hear what you're working on. And so whenever you've got something really cool you're working on, whenever you've got a publication coming out, come and email me. My email's at the top, and let me know. Or you can always ask Alan, anybody, and we're easy to find. And we would love to get you on some various podcasts. These are just some of the podcasts that we've got going on. We have connections everywhere, and the stream asked for me to be hooked, so I had to keep talking until he was ready to hook me. The stream says, thank you.
I'm Cindy Little, and I work on the ChemCam instrument on the Mars Curiosity rover, so I'm an engineering operator on that instrument. And ChemCam is a pretty cool instrument up on the mast of the rover there. And we shoot rocks on Mars with our laser. We go pew, pew, pew. And now that we have nothing but women on my team, we actually say pew, pew, pew a lot more often. So, because nobody laughs at us at work. So this is my group having pajama party because we had a very late start to our day. And you can see that I had the best pajamas. But the thing about this, we look like we're watching a cat video on the internet, and in fact, that's what we were doing. But we also shot that really cool rock, which was called Bad Call, and we were very excited about that rock. So.
Hi, my name is Dave O'Brien. I work on a number of different topics. The first major one is terrestrial planet formation, performing dynamical models to see how the early stage processes in the solar system build terrestrial planets. And in particular, looking at how water gets delivered from regions outside of the terrestrial planet region, the asteroid belt and beyond, how that gets delivered into the terrestrial planets as they grow. And then we combine those with geochemical and cosmochemical and geophysical constraints to try to build a picture of what the best fit is for where the Earth's water comes from. Short answer, mostly asteroids. The other main thing I work on is asteroid belt evolution and dynamics. That's kind of what got me into the terrestrial planet formation. And that got me into working on the Dawn mission as well, which unfortunately is over now, but we have an awesome data set that's there to keep using and hopefully get some funding for through DAP. Yeah, those are my main things. Since I have plenty of time, because there's nobody else left, I'll note that I learned a lot of...
And this has been the lightning rounds from the Planetary Science Institute retreat at the Hacienda del Sol Resort. Thank you, chat, for your amazingness. Those of you in the audience didn't know, but they were taking bets on whether or not you would finish and made donations when you finished on time. So thank you, all of you, for finishing. Thank you, audience, for being here. And remember, subscribe to twitch.tv/CosmoQuestX.
We're in a whole new world now.
Oh, okay. Well, now we...